So this video will cover an example with Gauss's law, specifically the electric flux on a Gaussian surface. So our goal here is to analyze the expression for Gauss's law in order to answer two questions. Number one, what can we say about the flux on a Gaussian surface as a whole given some enclosed charge? Number two, what can we say about the flux at each individual point on a Gaussian surface given some enclosed charge? So let's begin with the surface as a whole. Remember that the electric flux passing through a surface is given by phi sub E is equal to the integral of E dot n hat dA. So E is the electric field vector, n hat is a unit vector that is perpendicular to the surface, and dA is a tiny little surface area. And when I integrate over dA, I'm basically saying I want all of the components of electric field perpendicular to the surface over the entire surface. Now, remember in class, generally speaking, we can simplify this expression if the surface is flat and the electric field is constant in magnitude and direction. And that's where that EA cosine theta comes from. But in this case, we are not going to simplify the electric flux. We're going to keep it in this form. Now, Gauss's law is equal to the closed surface integral of E dot n hat dA. And that is equal to Q enclosed over epsilon naught. The little circle on the left-hand side of the expression means that we need to integrate over a closed surface area. So for example, in the case with this cube, we need to integrate the electric flux over each of the 6 faces. Now, what can we say about the flux on the surface as a whole? Well, first, just reading the equation, we know the net flux is equal to Q enclosed over epsilon naught. That follows just from reading the right-hand side. But Q enclosed can be positive, negative, or 0. So that means the total flux through the surface can be positive, negative, or 0. Now remember, by convention, n hat points outwards from the closed surface. So if the flux is positive, then more electric field lines leave the surface than enter it. If the flux is negative, then more electric field lines enter the surface than leave it. And if the flux is 0, then an equal number of field lines enter and leave the surface. So after the analysis that we just did, it might be reasonable to think that we know something about the flux at each point on the surface. But sadly, life is not that easy for us. So for example, we might postulate that if the enclosed charge is equal to 0, then the flux at each point on the surface is equal to 0. Here is an example of that. I have an ellipsoidal Gaussian surface. There is no charge enclosed, and so obviously the net flux is equal to 0 at each point on the surface. But sadly, there is a counterexample to this. Suppose we enclose a positive and negative charge of equal magnitude, opposite sign. Here, the net flux at each point on the surface is certainly not 0. And the reason for that is we can add up the electric fields from each of those point charges, and we find that it is never 0. On the other hand, we might think that if the enclosed charge is non-zero, then the flux at each point on the surface is also non-zero. And here's an example of that. We put a positive point charge inside of a Gaussian surface. The positive point charge has an electric field given by kq over r squared. So it's reasonable to think that, hey, every single point on the surface has a non-zero flux, and that must happen in every case. But sadly, here's a counterexample. Suppose we put a negative charge inside the Gaussian surface and a negative charge outside. Now in this case, the electric field in between the two negative charges right in the center is equal to 0, just by addition of vectors. And so at that one point on the Gaussian surface, the electric flux will actually equal 0. So sadly, we really can't say anything about the flux at each point on the surface. So where does that leave us? Gauss's law tells us a lot about the total flux over the entire surface, but it tells us pretty much nothing about the flux at each individual point on the surface. So Gauss's law really is only useful if we have some sort of symmetry in the system. And the reason for that is we can figure out some relationship between each individual point on the surface and then use that to determine the electric field at each point.